Afternoon, everybody. We're going to do a short video on a Zener diode used as a voltage regulator. This is the symbol for the Zener diode, and we have a cathode and an anode. And in order for the Zener diode to work as a regulator, we have to hook it up reverse bias, which means we're going to put the positive connected to the cathode and the negative connected to the anode. The deal is that the Zener diode, when it's connected in parallel to the load, it actually regulates the voltage that the load sees. So it has to be connected reverse bias, and it has to be in parallel to the load. And doing so will then regulate the amount of voltage that the load sees. And the amount of voltage that this sees will be the same as the rating of the Zener diode. So in this case, I've randomly picked a Zener diode with a voltage rating of 10 volts and a wattage rating of 50 watts. That means that the voltage at the load will be the same as the Zener, or 10 volts. Now, the other thing that we need in this circuit is something called a dropping resistor. And the dropping resistor is added in series to both the Zener and the load. The purpose of the dropping resistor is that the voltage source always has to be greater than the Zener voltage source, which means that we have to have this voltage, a place for this excess voltage to go. So we add the dropping resistor. In this case, I've randomly picked 16 volts. So 16 volts is our supply. The load wants only 10 volts. That means the dropping resistor will absorb 6 volts. Let's look at some amperages in this circuit. Now, I've also randomly picked 50 ohms for the load. So if the load was 10 volts, 50 ohms, 0.2 amps would flow through the load. Note also that we're using electron flow. So the electron flow means that current will be flowing from the negative out and back to the positive. So 0.2 amps will flow through the load, and we can use Watt's law, P equals I times E, to figure out the maximum current that can flow through the Zener diode without it being damaged. 50 watts divided by 10 volts gives us 5 amps flowing through the Zener. That's an absolute max. So then if we add the 5 amps that can flow through the Zener plus the 0.2 amps going through the load, we'd end up with 5.2 amps as our I total. Going up to the dropping resistor, since it's in series with both those things, it's going to see all of that 5.2 amps, and that would be divided into 6 volts, and we would know that the size of the dropping resistor then would have to be 1.153, and that's the smallest resistor that you can go. If you go smaller than that, this current will go higher, and since this stays the same, that excess current would go through the Zener and potentially damage the Zener. Hope that is helpful.